So why don't we just do what we normally do and start reviewing? And, come on guys, so we talked about adiabatic. As I've been slowly building up this matrix of pain of what are all the conditions. Remember, these are all the extrema for a gas expands, a gas contracts. Remember that these are stand-ins for actual chemical reactions. A gas expands would be like a chemical reaction that produces gas. Of course, there's an expansion in both cases, so that's why we start out this way. There's 4 extrema about how this can potentially occur. But of course, the real world being a shade of gray, but whatever. You got to know the endpoints before you know the middle. Isothermal, we started with reversible and irreversible. We introduced when we did work very slowly or all of a sudden, and that's still true even with really up there. Yeah. Hey. Yeah. All right. So this is true no matter what. This is very quick. That's very slowly. This is very sudden. That's true in the adiabatic case. Remember, adiabatic is the magic cylinder has been wrapped in glass wool. So now remember that adiabatic means, and I'm just going to always say AD, means when you see that, always write this down. Sorry, therefore, always write this down as true no matter what. So that's just automatic. It's almost full credit. Now that's full credit. Okay, now you got full credit. This is automatically true, and it means that the system is wrapped in glass wool. Now, don't forget, because one of you was saying this to me during office hours. I know a lot of you. This is what's going to mess you up on the test if I ask like an explain the word question. Remember, this is a heat transaction, but what you're going to want to do when thinking about adiabatic, and again, you're doing this because it's on the test, you're going to say, well, there's no heat, so there's no temperature change, right? Well, no, okay, you're wrong on 2 fronts. There's no heat exchange, right? Remember, there really is no heat. There's only changes of heat because it's inexact. There's no heat exchange, so there is guaranteed to be a temperature change. And if you really get cross-eyed, of course, it has to be the opposite of isothermal, which by definition, there's no heat transaction. Okay, now remember that also you need delta T. This is what you must. You've got 1 point here, but you got a 10% now, and you need 90 points more. You need delta T, and we do that by this little funky graph. As always, change of U is the bottom. If you don't get the change of U, you're going to blow the rest. Not that you won't get partial credit, and we explain this by using the fact that U is a state variable, and we can figure out what the change is as long as we know the endpoints, but how we get there is irrelevant. So we can use Yoda force and make the magic cylinder do things that it can't do, like in this case expand isothermally, which of course has no change in U. And then we can keep the volume constant and change the temperature, in which case I know that that's the change in U, which ends up being the change in total U. Now from there, again, I'm still reviewing. We set up this equation, which is true whether we're irreversible or reversible. Whether we're reversible or irreversible, we have this. Then we have to kick in whether we are reversible or irreversible. And if we're irreversible, remember that this is the one that is deceptively easy. This looks like it's incredibly easy, but it's actually horrible. And just look at your previous notes if you don't quite recall why that is. Actually, the reason is that you have to have one equation can only have one unknown, and it looks like you have a few. So just recall your notes. And the one that looks harder but is actually easier. Now remember that we're just getting to the change in T, right? Once you get the change in T, you've got everything else. Here's change in U. And I'll cover all the rest, blah, 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 blah. Again, we're still trying to get change in U, change in T, and then all the others. And, sorry, I am gone blind. So what I call these the adiabatic equations of state. There can be several of them, but the ones that we generally, I will give you, and I really can hear you quite well, by the way, and I even recognize your voice. Anyway, you guys have been pretty good up until today, so how about not? Anyway, so, I'm sorry, there's a couple of these, and so my head sometimes I start remembering what they are. Okay, TF over TI to the CV over NI is VI over VF. Now, remember that I derived it in class. It was definitely, in case you're wondering, that's at the far end of what I would ask as a derivation question on an exam. It was definitely about 1 or 2 more steps than I would normally like to do. It was up there in terms of steps, but it was down there in terms of easy, and I did it in class, so I had used this on tests before. Regardless, the whole point is, I have given you this information in some form or another. I have not given you TF. You calculate TF, you got delta T, and therefore you know that the change delta U, I'm not using a little partial, the change in U is CV delta T, again ignoring the heat capacity, that heat capacity is temperature dependent, just ignore that. It was on your last homework, but I don't think I'm ever going to show that again. And then of course delta H. Actually, I have to admit, I'm blanking out if I showed you this. Of course, it's the change in U plus the change in PV. And unless I'm being a horrible jerk, this will be the change in U defined above plus NR delta T. Okay, that's for a perfect gas. If it's a real gas, then it's a little bit harder, but anyway, you have that on the homework. Notice that you can actually turn this into CP delta T. And maybe I'll put that on the test, but that's because, remember, if this is CV delta T plus NR delta T, you can factor that into CV plus NR delta T, and that's CP delta T. But anyway, maybe I'll put that on the test and give you a break, but that's relatively easy. I also recall that I showed you a little bit about how you can plug in the perfect gas law for the volumes, and then you can turn this into a function of T and pressure. That's one of your present homework questions. And I also put a handout. I put a handout for this derivation because I don't want you to miss a beat. That's kind of an important one. And sometimes when you come to office hours, I do notice that you kind of freaks me out. I notice errors in your notes, and I'm wondering, did I do it or you do it? And no telling, but regardless, big derivations, I will provide handouts. I'm not going to tell you ahead of time. Big derivations, I give handouts because I don't want you to be missing an N or a -1 or blah, 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 and then get kind of cross-eyed. Okay, so again, big review from last time. We're all okay? We're set. So new material, which always takes me about half the class to get to, is actually, so you have definitely noticed this now. I ask leading questions on homework. I ask you questions that are like, what the heck? Because it's going to be on the next lecture or the next homework. Okay, so Joule's experiment, and I'm struggling to spell it. So James, I think his name was James Joule, and Lord Kelvin, Thomson, I think was his name. They were figuring out a lot of this stuff, and they wanted to know whether they were right, because it all makes sense, but in all physical sciences, right, we always have theories that make sense and then they fail. When you have one you think is right, you need to test it with stuff that you haven't done yet. And so their idea, Joule started this first, was to take all this delta H and delta U jazz and build a crazy device that would test what they were doing. And of course, if it works, the theories are correct. If it fails, the theories are not. That was the idea. So we're going to spend today analyzing adiabatic systems, because that's James Joule's crazy gas expanding mousetrap, and then I'll show you one more. That's what we'll be doing today. Also, I'm going to be doing a lot of derivations. I don't plan to put them on a test because the derivations we're going to do today, du at constant t and all that, are pretty bad. But anyway, okay, so Joule's experiment is a famous experiment that was largely designed to test whether any of this was right. And what he did is going to sound familiar. He had a bucket of water and a gas in a bulb. And so what do I call this? I don't think I call it anything, so let's just call it P1. And connected to that in a valve is a much larger container that is under a vacuum. Okay, vacuum. Sound familiar? Yeah. Some of you actually got this completely right when you were asking me about this. So remember, it's in water. That doesn't really, yeah, I can hear you better than anybody next to you can. Anyway, so there's a thermometer. It's like the world's worst thermometer. And when you see me doing this is glass wool. You know what that means. I already told you that everything is adiabatic. But remember that I will often not tell you that a system is adiabatic. I will tell you it's wrapped in glass wool, so you're not just trying to remember that that word means that you use these equations. That word means that it means something to the experiment. I can touch this object, and this object is the shape and form that it has because the system is adiabatic. It's wrapped in glass wool. So anyway, if I ask you a question about this, do this immediately, right? That's always a point. 1 point out of 10, so that's not bad. Okay, so what Joule does is he's got a gas, and it's under high pressure, and a much bigger container connected to it that's under vacuum. And it's kind of obvious what he's planning on doing. He's going to open the valve. The gas is going to expand. It's kind of practical. You see why it's wrapped in glass wool, because probably you're imagining it's going to cool. That may not quite be true, by the way. Just wait. You imagine the gas is going to cool, and of course the water will then transfer heat because the system's adiabatic and you're measuring the temperature of the water. So now he can figure out whether the water gets hot, the water gets cold. Right, it's kind of obvious. Now notice that this is kind of a funky thing. Why any of this? He can just do this with the metal magic cylinder and just hold on to it and see whether it gets cold or warm or whatnot. Okay, so I guess I just need to do the derivations. Let's see. Okay, so we've done this, but now what's the change in work? This is already, hopefully you already know the answer because it was on your homework. Zero, right. Expansion into a vacuum is 0. And let me explain that in case you, to be blunt, you got it wrong. The change in U, of course, is the change in heat and the change in work, and so that's 0. So this is an iso-internal energy transition. So remember, I told you, I'm always going to ask you, what's the change in blah with respect to blah, constant blah. And constant blah is often constant pressure, constant volume. That's still going to be true for most of the class, but this guy, I don't know what he was smoking, but he made the same thing that everyone at James Schuylkill Towers is. Every time I walk by at night, I was like, never mind, sorry, I'm going off on a tangent. Ever since they legalized medical, Jesus, I live right by the dorms, and man, I'm glad they don't drug test. Anyway, so this is going to be constant U. We're going to analyze this at constant U. That's why this is really weird, by the way. Constant volume, constant pressure, makes sense. Constant pressure in a balloon. Constant volume, the metal box, totally makes sense. Constant U, yeah. What's he was smoking? Okay, now in case you were not sure about this expansion into the vacuum, I like to try to help the graphical people. Remember that we looked at P versus V originally for work, and I showed you how an expansion, you drop from a high pressure to a low pressure, and then you expand, and how integrals are, of course, areas of the curve, and there's minus that area is the work. But the funky thing about this is that the external pressure drops to 0. And yes, I know the pressure rises as the gas is going into it. Look, I don't know. Let's not just go too nutso or overthink this. And the reason I'm not worried about this is because really, you just make this vessel really small and this really big, and it's just not that important. Now here's a nut. So graphical people, there's for you people who like to think about molecules, let me explain it this way. Now, in this bowl, gas molecules, if you could look at them, they look like a bunch of bees, like a huge number of bees, even if there's not a lot of gas. If you look at the actual gas molecules, it's like a gigantic number of crazy bees, and they're bouncing all around like mad. And of course they hit the valve, they bounce back, but when the valve opens, here, let me just draw that. So here's a bulb, and here's the other bulb. The valve is now open. So that's kind of like that. It's kind of like a little slot or something, and it's now out of the device. And I'm obsessing with drawing this perfectly. I don't know what the heck is wrong with it. But anyway, okay, so this little coin type of thing is moved out of the way, and a molecule that normally would have bounced off, it just keeps going. Right? That's expansion into a vacuum. How much effort does that take? None. Right, it just keeps going. So that's why there's no energy change. That's why there's no work. because it doesn't actually do anything. It just keeps going. Why would that take any effort? So anyway, that's why the change in work is 0. And all right, so now that I've established that, what the heck is he trying to do? Of course, now you got to take into account, now remember calorimeters, and when you were in high school, if you went to a fancy pants high school like I did, I went to actually IMSA, if you go to IMSA or you know about IMSA, your school is modeled after mine, North Carolina. I went to North Carolina IMSA, you probably already knew that. And so in my fancy pants high school, we actually had a professional calorimeter, which are really expensive, and you had to determine the calorimeter constant. Anyway, these actually can be decently complicated, but what he's ultimately trying to do is get the change in temperature of the gas in this funky device. Right, so he's looking for a change in T. Now the change in T is occurring because of a change in what? Let's not quite. Now remember, U is friends with what? V or P? V. Right. V is its natural variable. Besides, he built the thing. He knows exactly what the volumes are. Okay. Now, as always, I need to hold something constant, but I've been blabbering about that for 5 minutes. What do I hold constant? No, pressure is definitely not held constant. U, right. You see, this is a really strange thing to try to ascertain, but that's why he did it. Right. This is weird, but if his series are correct, he's going to get the right answer. He's giving it if you have a theory, and it explains cars going down the street, and you test it against cars going down the street, it's probably going to work. But does it really work? What you do is you test a car going up and down a hill, right? Then you know whether your theory actually works or not, or is it just some kind of fluke that happened to work. So, okay, so now we're gonna get to this. Let me erase it to give myself room for the ultra long derivation. And remember, this is a good third of the class of these derivations. And how do you know how to start? I generally will tell you on the test how to start, because you can start analyzing changes and things with, you can start with anything really, and you can expand it in terms of anything, and you can get to the right answer. It's just a matter of how many steps does it take. Oddly enough, I start with the fastest, the easiest way. And so on the test, if it's ambiguous at all, which it almost always is, I'll give you the push in the right direction. Because I would think I would start with change in T, and that just wouldn't be right. I could, but it would take forever to get to the answer. This is going to get the answer very quickly. And you also got to know what variables you want to change. Well, I've already been talking about changing volume, and I'm going to do that. Of course, I have to do that. Now I have to decide what to hold constant. And I'm looking at my notes because, in all honesty, I just don't know off the top of my head what's the easiest way to do this. And another thing I do every time is don't give myself room. Now remember that when you've decided this, it automatically determines the next term. Then if you're going to hold temperature constant, then you got to let it change. What's held constant is what was not held constant last time. Of course, these cancel, changing U, This is all pretty sensible. And now what I want to do is, again, because I know what the answer is, I'm going to divide by, let me see how I can show you how to get to the answer. Well, I could divide by anything I want, and what I'm trying to get to is dt dv. Now, given I happen to start out this way, which again, I kind of have to push you in the right direction to do that, I'm now looking at this, I'm looking for the answer to the thing I asked, which is dt dv. Okay, I got half of it right here. Now, to get to dt dv, I'm going to divide by dv. All right, now I've got to divide the whole thing by dv. Constant t, dv, dv. You know what's going to happen with that. Oh, you know what? Hold on. The UDT at constant V, is that familiar? Can I simplify that? Well, not simplify. Can I give it another name? Right, CV. I like that because it's just a lot easier. That's correct. Okay, now what should I hold constant? You got to do that, by the way. Sometimes it matters, sometimes it doesn't. Remember what we were looking for? The reason I erased it is to see if you remember. What should I hold constant? Hold U constant, right. Hold U constant. Remember to leave this alone. Just like you leave this alone. That's a number. What can you do with it? Nothing. Okay, all right? And there's my answer. Now I just got to do some more simplification. I see 2.
dv over dv.
Okay, that's 1. And
dv
huh?
Over constant.
This one?
Yes.
Changing U at constant U is 0. Of course it's 0. Now, okay, now some of you probably have realized that there's another little trick I could do. And what do I want to do? I'm going to bring this guy over and do 2 steps of algebra, and I'll raise this up in a second. I know you probably haven't trouble seeing it. C, G. Okay, sorry, my handwriting's a little, here, I'll toss this up here. I got a little bit more to write, but I just want to look at this. Okay. All right, so that's basically it. There is a little symbol for what's called the Joule coefficient, which is a thing that gives you it's just a symbol that you associate with the constants that are used in this crazy little experiment. But I want to look at this real quick and just tell you that Joule did this experiment and he got nothing. Actually, here, let me write that Joule coefficient, because remember, we're really looking at dTdV. Sorry for my weird juggling of the algebra. And it's dTdV at constant U. It's given this funky little symbol, micro, I don't know what that is, micro, and of course it's minus 1 over CV, du dV at constant T. Okay. Now, I did actually hear one of you tell me to simplify one of these terms. Which is it? Okay, what should I simplify it to? It don't, by the way, but 0, right. Changing U at constant temperature, right, by the equal partition theorem for a perfect gas. In fact, you are going to do one of these types of derivations and you're going to prove that. It's unfortunately kind of complicated. It's one of the harder ones you'll do in about a month. Regardless, perfect gas, this is 0. So James Joule, when he built this thing and made temperature measurements, nothing happened. Actually, it took, oh God, do I have that? I believe in 1933, someone actually just simply had better calibrated, more sensitive devices, better temperature probes, and they actually did measure a change in the temperature of the gas, but it was really slight. In other words, it was not quite 0, but basically 0. And when you do this derivation, you're going to find that for a perfect gas, when you do the derivation, it will be 0, and if you do a van der Waals gas, it will be, like the A constant or something like that. I don't quite remember, but anyway. So it's not really quite 0, but it's awfully close to 0. And remember that James Joule would have been using nitrogen gas, which you recall your compression factors. Nitrogen is about as perfect as a real gas gets, which was great for figuring out PV equals nRT. What was bad was trying to figure out whether you actually should measure something or not. So look, the guy was actually relatively happy because he knew he should get he knew that he should see almost nothing. But unfortunately, he got absolutely nothing. So he actually goes on to build a better mousetrap. But before, that's the Joule-Thomson experiment. Don't write that down because I want to do some more analysis of this stuff. Okay, so the test, which is a week from now, has a unit section. I give you this information. What are the units of the Joule coefficient? What are the units? Kelvin over volume would work. You could also, look at this, right? So you know that. You know it's close to 0. Let me tell you why, ultimately, these people in 33 This is like 1880 or something like that, I recall. Why is it not actually 0? And I'll do this graphically, and again, I've already said, you're going to do this, you're going to do a derivation, you're going to figure out exactly what it is. Let me do it graphically before we do a derivation. It turns out that, I guarantee you in some way, shape, or form, this is on the test, so put a star by this. Perfect gases differ from real gases in that perfect gases don't interact, right? They don't hit each other because they don't have volume. Perfect gases do not have volume, so how could they hit each other? And perfect gases don't attract each other. Real gases do. Now, so what happens is when you're at small volumes, you got a finite amount of gas at a small volume, they are attracting each other, and that will change their internal energy. Now, it turns out that most gases do this. Now, eventually, of course, you're at very large volume, they simply never find each other to interact, and so this is most gases, but we got two weirdos that do the opposite. They do this. So when they get together, they don't like it. So again, I'm using personal words for objects and ideas, but going downhill in energy, that's good. Let's call that good. And for two examples of gases, it's bad. They don't like to be next to each other. Anyone remember what those two gases probably are? Yes, hydrogen and helium, let's call them the haters. The haters, that's hydrogen and helium. Because they just don't, they're like little billiard balls, they don't really attract each other, but they do whack into each other, and so that's bad, right? So it makes sense that they don't like to be next to each other. Okay, now let's say I give you, I'm really thinking about doing this, let's say I give you a graph like this, and then I tell it, now I'm asking you whether this should be positive or negative, right? I warned you many times, I really like to know whether things go up or down, because when it comes to delta G, when we do chemical reactions, delta G better be negative or it doesn't work. So I'm obsessed with, does it go up or does it go down? Is it positive, is it negative? So I want to know whether the Joule coefficient is positive or negative for most gases. Okay, to do that, any guesses? Offhand, all right. U versus V, Joule coefficient. Any guesses? None? Okay, that's fine. Let's walk through it. Okay, so there's this guy. Forget this one. Let's not worry about that. I haven't given you data on T versus V. I gave you data on U versus V. Okay, minus is minus. Let's do CV. Is it positive or negative? It's positive. All right, what about for hydrogen and helium? What's CV? What? Positive. CVs are always positive. Right, remember, if the heat capacity of something was negative, that something's just shedding heat like mad all the time. Right? It's a perpetual motion machine. Negative because of the minus sign, positive. Okay, du dv is the slope of this line because I'm asking about most gases. Positive or negative? Of course it's positive. And the result is negative. Right? Expect me to do something like this on the exam because, I mean, geez, it's actually really easy, okay? And this actually has implications in refrigerator design. Again, Joule didn't measure anything, but other people did come along and they did find that there was an effect, and all of this actually does add up. It's very small, as it should have been, but it ain't 0 either, as it should have been. So we're feeling really good about all this thermojazz. All right, with that, let's drop it just like James Joule did. And it's kind of a neat name, it's like Jesse James. Anyway, so Joule then gets together with J.J. Thomson, oil can guy. I think that's the same as Lord Kelvin, I'm pretty sure. And there's not a P in his name, it's Thomson. The guy's name is the most misspelled of any scientist next to Einstein. So they team up to build a better mousetrap. Here's the thing. The Joule coefficients are not 0, but they are shockingly small, so they built a different mousetrap, and this is called, cleverly enough, the Joule-Thomson. Right? No S, no P. I have to remember that myself. Joule-Thomson experiment. Okay. And now you can imagine, because actually some of you almost got it, we're going to build a mousetrap to measure the change in temperature of a gas as what changes? Right, because I just did volume, let's do pressure. What do you think is going to be held constant? What's pressure's friend? H. Right, H. It's H. H's goes with P's and U's goes with V's. Now I can still totally do this for you. There's nothing illegal about that. It's just that whenever I see H's, I see P's. And whenever I see U's, I see V's most of the time. It's weird how that happens. Anyway, remember natural variables and all that. Blah, 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 blah. Okay, now, here's the damnedest thing. I showed you how to build a constant U mousetrap. Now you got to do a constant H mousetrap. And that is not the same. It's not like, oh, well, you just have to heat the water. No, this is actually a real knocker. All right, I'm going to draw across the board how this device works. It's considered one of the more clever things humanity has ever done. It's a cylinder, and it has two plungers, so it looks like I'm going to be doing some kind of work. So let me draw the two plungers, and of course there's a little stick at the end where you manhandle the thing and move the thing in and out. And of course there's getting an end to this. My drawing skills aren't too bad. Okay, now here's the thing. There's a weird little device in the middle of it. And I explained this little device, and then there's another plunger. And here we go. Okay, all right. Now, so that you can kind of follow what the heck is what with this not the greatest drawing in the world. These are the plungers, and there's this weird little device in between. And what this is it's like a zeolite. Have any of you ever heard of a zeolite before? Well, zeolite is a mineral with a bunch of holes in it. And they're usually made of SiO2. The way it's in your book, by the way, it's a porous plug. But that's like a zeolite. And again, a zeolite is a solid object that's actually full of these molecular-sized holes. One reason you should know them is that that's what the oil industry uses for all its catalysts. That makes sense, right? It's a small object, but with a gigantic surface area. It has an inorganic matrix, which is relatively resilient. SiO2 is dirt. It's okay to throw dirt into chemicals that usually they get a little dirty, but that's actually not so bad. And then what you do is you put catalysts inside of the SiO2, which again is not particularly difficult. What you do is you take these and soak them with like iridium or platinum, and then you throw all these chips into a reactor bed, and they do whatever they do. So anyway, so you have this porous plug, and what this is going to do is that as you push one of these cylinders closed, the other one's going to open up. But what happens is it's like a stopping power. So you can imagine what you could do here is add 4 atmospheres of pressure because you're pushing with 4 atmospheres of pressure. But the person on this side is pushing but with 2 atmospheres. Right? So you see, it's not. Remember that when you're pushing the magic cylinder, if I push with 4 atmospheres, it's going to be under 4 atmospheres as I push the plunger in. This device can take this side at 4 atmospheres, and we can end up with the thing at 2 atmospheres smoothly. And that's what this porous plug does. I think it's not too hard to imagine that. Let me draw that then. What happens, and so the conditions are P1, V1, T1. And of course the system is adiabatic. So glass, wool. Now, of course, if I tell you something has glass wool on it and you screw up and you do all the question isothermally, that's a point. I mean, it should be 10 points, but I'm not that horrible. So anyway, that's policy on when you make that kind of screw up. Just like if you miss delta T on an adiabatic question, which technically you got everything but DQ wrong. You would have to have gotten everything wrong but DQ. It'd be impossible not to. Regardless, what we do is we look at your change in temperature and we back calculate everything else. And if you got everything else right with the wrong temperature, we actually give you a break on the, we just count temperature wrong. So no, stop praising me. Stop it, it's too much. Okay, so anyway, here's the glass wool, and of course there's a thermometer in there somewhere, and of course you're going to end up at P2, V2, P2. And hopefully my analogy is, I hope you follow along that I look at this, bad as my drawing is, I do see how a person could apply 2 atmospheres of pressure on one side, and, 4 atmospheres on this side, 2 atmospheres, and there'd be this smooth transition from one side to the other. Okay, so now the question is, sorry, this is my OCD taking me, and I have to finish it or the roll will explode. So I don't know why I'm like that. Oh, mental illness, that's why I'm like that. Anyway, okay, so drawings come, except for this bit right here, then the world will explode. So, all right, that was the device. Sorry, I've been running my mouth like an idiot. But now I have to prove that this crazy contraption is actually iso-enthalpic. That's the word. It's on the test. It's not on the test. You know I don't care about words because I can barely speak sometimes. Okay, so let me put this up here and let's do the derivation to show it's iso-enthalpic. Then we're going to do the dt dp at constant h. I'm going to give you some experimental data. Of course, it's also that's the Joule-Thomson coefficient. It's also small but not 0. And yeah, that's about it. Then I'm going to return your homeworks. Your homeworks, by the way, 95%, much better. We did 85%, so very good. Okay, let me start here because this is a little bit on the longer side. We're going for 10 minutes. Sorry, I've been running my mouth. Remember that the change in U will be the change in one side plus the change in U of the other. So when I say U1, I'm talking about this guy, and U2 is that guy. And this is actually rather easy. Final minus initial. Let's just do this. Plus. Remember that the final state on the left, there's no gas. No gas has no energy. It initially started out at U1, final minus initial. Now the gas on the right ends with the U2 amount of internal energy, but it started out, there was no gas there. No gas is no energy. Right, so remember that this is delta U, and of course delta U is therefore U2 minus U1, which also makes sense. Final minus initial. I'm just verifying that. Okay, now here's the thing. U1 changes due to work, right? There's no change in heat. I'm not going to write that down because I wrote down glass wool. But U1 changes due to heat. And so let's do that. Let's do the change in, I'll put it over here so you can get straight. Again, I need to integrate the work on the left-hand side. And to do that, of course, I have to integrate volume. I initially am at V0. I will end at no volume at all. The pressure was maintained at 4 atmospheres. That's P1 and dV. And to do the integration, that's going to be plus P1 V1. And I'll link that up to you. All right, so, all right. P delta V, 0 minus V1 is minus V, minus P1 V1. Okay, anyway, I leave that to you, it's not that hard. Let's do the change, let's integrate the change in the right-hand side. And of course, this is pretty easy. It's basically, it's this, and so all you're going to get is a minus sign, and of course, it's going to be P2 and V2. There you go. Okay, so let's go back here, because the change in U is only the change in work. Sorry, here's another little factoid. I know we haven't covered this. Sorry. But energies add always. And that's also nice because I know that areas add. Integrals add, energies add. If they happen to be positive or negative, that's another issue. But I know that energies add. So this change in U, which is just almost by definition this, has to be equal to the change in work. That's all that happened. the change in work is, of course, add them together, P1 V1 minus P2 V2. Therefore, U2 plus P2 V2 is U1 plus P1 V1. Which of course is delta, which means, sorry, H2 is equal to H1, and there's no change in H. So that's all there is to it. Okay, 5 minutes left, so let me cover the dt dp, and I'll throw some data there. I do need to finish this, so sorry I'm going to have to rush a little bit. I thought I did a little early, but as usual, I talked about cats and stuff for Game of Thrones. Actually, I didn't. I don't know what I talked about. I actually do watch my own videos to critique myself. Okay, so to finish up the discussion of the Joule-Thomson experiment, of course I'm looking for this. I see that I can build a device that does it. Now, this derivation doesn't, you don't really have to have this device in your head to do this. As I've already stated, I'm going to start with the change. If I'm doing P, I'm going to start with the change in H. And of course, I have to let the function change. Guess what I'm going to I'm going to think about changing temperature at constant pressure. And again, now remember, like, how do I know how to start this way? Because I know the answers ahead of time. To be blunt, that is true. And on a test, I would tell you to start this way, otherwise it would be hopeless. Okay, now of course, I see a dt, so I'm going to divide by dp. And yeah, dp. So dh, dp, a constant p, dt, dp. Okay, then I've got, recognize this. The HDP is what?
CP.
Right, CP, just like last time we had CV, DP, DP. Wait, I have done something wrong. No, that's D. No, this is, what have I done? No, this is C. My bad. It's right here. Right here, this is CP. Sorry. Sorry about that. Yeah, but it's a miracle I haven't screwed up yet. Okay. Now, notice I haven't stipulated what's held constant. Sorry, in the interest of time, obviously H is held constant.
Zero.
Right, now you don't have to worry about perfect gas, this or that here. One, right? That doesn't matter whether you've got a perfect gas, this or that. Okay, so therefore the Joule-Thomson coefficient, which is dt, dp, I'm just going to go ahead and do the algebra in my head. Because it basically looks exactly the same thing as the Joule-Thomson, except I got h's and p's, and that's minus 1 over cp. I'll toss this up, I know you're having trouble seeing it. The h, dp, at constant c. Constant T. There you go. Now, again, I know I've been saying this a zillion times. H should not change with T for a perfect gas. Guess what? You're going to derive this sucker too. When you do this derivation and you plug in PV equals nRT, you're going to get 0. When you do this derivation and you plug in P is RT Vm minus B, but when you plug in the van der Waals equation, you will not get 0. How big is it? Here's just something, I just want to end with this, and I'm going to return your homework. And of course, I found this on the web in kelvins per atmosphere. Sorry. The thing that's really neat about this is the thing that's going to blow your mind. Notice that I've written Freon. Notice that it's positive. Ammonia is also a relatively big positive number. Air is smaller. This is the cool thing. Hydrogen and helium are negatives.
It's supposed to be HE, not H2, right?
Oh, yeah. Thank you. You doubt my spelling. Anyway. Okay, so again, hydrogen and helium are weirdos, but I want to point out something that's kind of cool. If these are negative, when you expand hydrogen and helium in this mousetrap, do they get hot or cold? No, you're thinking of most gases. Expanding gases get cold, unless you're hydrogen and helium, they get hot. Right, expanding gases, if you're weirdos, only these two, they actually get hot, not cold. All right.